Let's use the change of variables theorem to compute an area. In this particular problem, we're asked to compute the area enclosed by an ellipse. So we can utilize the general formulation that was learned in pre-calculus. That is, you derive this equation for the actual curve of an ellipse, and we just assume that a and b are positive, and we have x squared over a squared plus y squared over b squared equal 1. And using the notation of the double integral, the area of R would just be the double integral of the area element over the region R. It's that simple. Now, because the region R maybe isn't as simple as we would like, we're thinking there might be some transformation that would allow us to replace R with a simpler region S, and that's exactly what we want to do in this example. And the transformation is actually quite simple. So we're going to define a transformation from S into R, S being the region that we're trying to figure out in terms of new coordinates. And so we have T of UV is equal to AU comma BV. That is, X is equal to AU and Y is equal to BV. And so we've actually tied this transformation back to our equation for the ellipse. Now, as simple as it looks, we can now look at X equal AU and write U is equal to X over A. And we can look at Y equal BV and write V is equal to Y over B just by division. But now again, we look up here, X over A can be substituted. That is, X over A squared is just U squared, so we have U squared here. And Y over B here, this term, squared, is just V squared. So what we have done with this transformation is that we have transformed the region R into the unit circle. That is, U squared plus V squared equals 1 is just the standard unit circle. And what we're doing is we're enclosing the area of the unit circle. So we get this nice curve, which is simple, and we have the region enclosed by it. So with this transformation, all of these interior points get moved to the interior of the circle, and the elliptical curve becomes the circular curve. So that's really a rather elaborate manifestation of a very, very simple transformation. So as I've written over here in blue, this is a simpler region. So now all we have to do is use the theorem. So for instance, this is written just like we need, so we can do the Jacobian here. So when we take our U partials, we get A in the first coordinate, but 0 in the second coordinate, so we have A0. And then we take our column for the B partials. For the first coordinate, we get 0, and for the second coordinate, we get B. So we have 0B. Now when we compute the determinant, we just have the cross here, crisscross, but we just have the AB minus 0, so this is AB. And this is what we need in our change of variables theorem. So now we're almost done. The area of R can now be replaced using the change of variables as the double integral over S times the absolute value of the Jacobian determinant integrated with respect to the area element. Now we just computed this. This is just a constant AB which we can extract. And so what we have here is what's mimicking here. That is, this double integral represents the area of S. And so we can exactly write that. This is AB, excuse me, times the area of S. But we know what the area of the unit circle is. That's just pi r squared, but the radius is 1. So the area enclosed by the ellipse is actually pi AB. Now I'll tell you that there are other ways to actually do this computation, but this happens to be probably one of the simplest ones. It just really depends what you know and what you're working on at the time. So now we have a very elegant application of the change of variables theorem to determine the area of an ellipse, and now you know, and we are done.